Now, I'm sure we're all aware of compounds, atoms, molecules, and whatsoever, but how do these things actually stick together? What is the glue that allows all of these compounds to stick together and work and make it a whole? Basically, what there is are forces. I always do that. Forces. Now, there's two types of forces. There's intermolecular, you'll see why I did that Y in a second. Intermolecular and intramolecular. Now, I don't know why they've made it like that, but just if you get the hang of it, you'll know which one's which. Now, you've probably learnt about intramolecular forces already, as they are just the ionic and covalent bonds. Intramolecular is just the bonds formed like inside a compound, atom to atom. So if you're doing, say, C2H4, there would be CH. This is an intramolecular force because it is a covalent bond. Now, intermolecular forces, on the other hand, are also known as van der Waals forces. Now, if you look on any other internet research, YouTube site, or whatever, they'd be referring to van der Waals forces as the weakest type of intermolecular force, which is the dispersion force. Dispersion force. Now, the reason for that is because in the past IB syllabuses, for example, the current grade 12s that are going through now, they have been taught that dispersion forces are van der Waals forces, but in our 2016 new syllabus, the IB has changed, referring van der Waals forces from this to the whole region of intermolecular forces. I don't know why, but just keep that in mind. Now, dispersion forces have many other names. They're also known as London forces, or this is a long name. I'll just pause it and write it down. Instantaneous dipole to instantaneous dipole. Whew, that's a long one. Now, the second strongest is just dipole to dipole. And the strongest intermolecular force is the hydrogen bond. Oh, my stylus is stuffing up, I'm sorry. I don't know. Oh, maybe I'll zoom in. Sorry. Okay, hydrogen bonds. And hydrogen bonds are present in lots of places, and there's 3 types of hydrogen bonds, and they are from strongest to weakest. There's, oh my lord, there's OH, NH, and HF. Now, for hydrogen or dipole-dipole forces, there has to be a polar. It has to be polar. And this is because, for example, say water, I'm sure you've all seen this before, but water, there's oxygen, hydrogen, hydrogen. Can you name that one? What type of force is that? That's an intramolecular force. And what type? It's a covalent one. Anyways, now the reason why basically the hydrogen bond exists is this is delta. Oh man, I'm a bad drawer. Delta positive, this is delta positive, and this is delta negative. What that basically means is that there is even though the electrons are distributed evenly, and this has 2, this has 2, this has 8, it's because oxygen has a higher electronegativity and its need to have electrons is more, so it kind of like hogs the electrons, and thus it has a more negative pull. And say there's lots of like water molecules around, just floating around here. What happens is it instantly, this negative, this positive, it makes its way to here, and it ends up being that it looks like this. It goes and see this right here? This is what we call a hydrogen bond, and that's why the surface tension of water is very high and it's able to keep its resistance because of these hydrogen bonds being everywhere. Now for dipole-dipole moments, it's just, we need to first check if the atom is asymmetrical. So take CH4 for example. CH4. Even if all of these, that was a really bad one, have delta negative positives, delta positives, and CH4 has a slight delta negative, because these all have equal forces upon each other, they just basically outweigh each other and they cancel each other out, and thus the overall arching molecule is not polar, even though the individual atoms are. On the other hand, let erase or no? Okay, if you take something like HC123N, then this, because we said up above that hydrogen bonds only happen to oxygen, nitrogen, or fluorine, that's because they're the 3 most electronegative atoms, then these don't come, carbon doesn't go in that category, so it's the next weakest force, next strongest force, or next weakest, makes sense, because it's the middle. So this is what we call a dipole-dipole moment. The same thing happens with what happens here, it's just that it's not as strong. To be in a dipole-dipole bond, it must be asymmetrical. See how there's 3 here and there's 1 here? That's what makes it uneven. Or you can have, what could you have? You could have NCl. You can't even see the dots. Jeez. You can have NCl3 where there is a lone pair, and thus, if you watch my previous video, lone pairs, because of the VS EPR theory, it states that lone pairs give more repulsion, and thus these would be pushed down. Even though it looks symmetrical, it's not, and because it's not symmetrical, it applies for a dipole-dipole force. Now, dispersion forces, remember not to call them van der Waals forces. Dispersion forces, think of it as Velcro. My teacher taught it to me as Velcro. Now, if you zoom if you zoom in a lot on Velcro, you can see that there's all these little hooks. And the hooks are what attach to this. So there's hooks like that. And what ends up happening is these two come together and they link. I'm not a Velcro expert, so I don't know how exactly they link, but that's just basically the force of Velcro. think of that as London forces. If we are given one hook and we are asked one tiny Velcro thing and we're asked to hook that up to another tiny Velcro thing, like, oh man, it would be really hard. You'd be trying for ages to just get that in, It would be really difficult. But if we were given a huge, say, meter by meter thing with all these millions of tiny Velcro pieces, it'd easily, without a doubt, attach to this, and it would be very difficult to take it apart. You'd have to put a lot of force on it. That's the same as instantaneous dipole forces, because in small amounts, they aren't very strong at all, but in large compounded molecules, then with multiple bonds, then it'd be stronger. So basically, the increased molecular mass is equivalent to an increased dispersion force. And that's basically it for forces. You just have to keep in mind that van der Waals forces were referred to as dispersion forces, but now in the new syllabus they will be referred to as van der Waals forces. So if you're doing old IB question bank and van der Waals forces comes in a question, just keep in mind that they are referring to dispersion, not the whole set. And that's just it. Thanks for watching.